Hello, I'm making this recording of myself solving a problem in algebra from a textbook by Herstein. I'll just quickly, it's called Topics in Algebra, here it is. And it's a starred question, although I think it's probably not that hard. And I'm interested to understand the thought processes that go behind, that lie behind how I solve it. So it's one of those questions where when I look at it, when I first look at it, I don't really see how the proof is going to go, and I want to see how I get from that state to seeing how the proof will go. So let me share my screen, or the relevant part of it anyway. Um, so the problem is the following. G is a finite abelian group. And it has the following slightly strange property, which is that for all n in n, the number of x in G such that x to the n equals e is at most n. And the conclusion we're supposed to draw is prove that G is cyclic. Now, I want to stress something here, which is that I think I can see how a proof would go, modulo working out some details, which is I could just use the classification of finite abelian groups to say that my group is actually a product of cyclic groups, and I can sort of search around in that product of cyclic groups and find myself, assuming that there's not just one cyclic group, or it's not a product of cyclic groups of orders that are co-prime to each other or whatever, so doesn't itself work out as a cyclic group. Search around for some n that gives you too many elements of that. So for example, if I take the cyclic group, actually I'm going to write this down because I think it's relevant anyway. So let's just have an example. This is often a helpful thing to do. I seem to have got stuck with an eraser, so let me just try and unstick myself. Oh, blast. Oh, I've remembered. Okay, I've just been a long time since I've used this software, so I'd forgotten how to get out of the eraser, but I've got it now. So let's just, so step one, let's show that, what I call this, find, it's not a sort of necessary step one, it's just what I'm going to do with my step one. So find some non-cyclic, but still abelian G such that hypothesis fails. So actually, what's one way of looking at what this step one is doing? Well, I'm looking at the contrapositive, which would say that if G is not cyclic, then the number of x, sorry, there must be some n such that the number of x, such that x to n equals e, is greater than n. And now I just want to say, well, I want to prove that for all non-cyclic finite abelian groups G, but let me just see if I can find a single example and learn something from that. So what's the simplest example I can come up with of a non-cyclic finite abelian group? I think it would be C2 cross C2. So what would be let's see, what would be a suitable number n? It can't be 1 because only the identity works. It can't be 4 because the group has size 4, and so there'll be at most 4 elements. So there's only one pretty obvious number to go for. Try n equals 2. And indeed, we have that. So if the generators are A and B, we have that A, B, and I'll write it in plus notation since it's an abelian group, all have order 2. And we see that we have our counterexample. By the way, yes, I didn't I meant to say this, I almost got as far as saying it, but this question comes in the book long before anything as advanced as the classification of finite abelian groups. And so that suggests that the question should have a solution that doesn't rely on that classification. So that's what I'm looking for here. So what did we do there? It's not very easy to generalize from that example because it wasn't clear what was going on, but let's perhaps try. So we can't do C2 cross C3 because that's the same as C6. If we did C3 cross C3, that's another fairly simple example. So if the generators are A and B, and it's a reasonable guess that the n that's going to work will be 3, then we can take, so A is a solution. Actually, I should have said, because it's not just having order 2, it's being a solution of x to the n equals e. So I could have added that e is also a solution. So in fact, there were 4 solutions in that case. So here we've got how many elements cubed to the identity? We have E, A, 2A, B. In fact, come to think of it, they all do. So that's sort of okay as an example. At the moment, I'm just giving, but if I give these examples, and all the examples I give will be products of cyclic groups sort of naturally. So it's difficult to see how I'm going to end up with a sort of insight that gives me a classification-free proof. So perhaps I should think about that a little bit. So I might prompt, or alternatively, if I just pursue this line of thought, supposing I'd never heard of the classification of finite abelian groups, I might just sort of think, well, I've got it for some products of cyclic groups, but they needed not to be cyclic. So I might ask myself, see if I can just prove it for products of cyclic groups that aren't cyclic. So then I would ask myself the question, if I've got let's call it M1 cross CMR, so when is it cyclic? That would be the, whoops. When is it cyclic? And so I've already seen in the case of C2 cross C3 that it was cyclic because it was generated by if I took a generator of C2 and a generator of C3 and added them together, I'll get a generator of C2 cross C3. And so inspired by that, I could sort of say, try AI is a generator. I'll put a colon here just to be clear. Is a generator of CMI. Then look at A1. No, get rid of that dot. A1 plus AR. And so when is, so this will be a generator. If for all sort of what should I call the coefficients? I call them T1 up to TR. There exists a T such that TA1 plus AR equals T1A1 plus plus TR AR. By the way, of course, I mean, I'm slightly conflating some notation here. So this TA1 plus AR, so I suppose what I should really call this, in fact, maybe I will change the notation to be a bit less confusing. I was imagining this a generator of the copy of CMI inside this product, but perhaps I'll just write it as, since that's a rather more standard notation. So this equation then becomes, I want, makes it a little bit clearer what's going on. So I want T of A1 AR equals T1 A1 TR AR. And I'm not going to write too much here because we see straight away that if for TA1 to equal T1A1, we need T to be congruent to T1 mod A1. Same thing for all the other indices. So need T congruent to Ti mod AI, and then we can use the Chinese remainder theorem to get that. So, sorry, we can use the Chinese remainder theorem and do this if no two AI have a common factor. So we don't have to worry about that case. So now let's suppose, so I'm doing it for products of cyclic groups, which unbeknownst to me, so to speak, is in fact the general case. So suppose that sort of D divides M1 and D divides M2. Right, if this problem is correct, then I should be able to find more than D elements of order D. And so how can I find at least some elements of order D? And I'm using order D not to mean strictly order D, but I'm just meaning that it's the Dth power is the identity. So let me just get a new page. I've forgotten how to do that. I think it's, there we go. So if D divides M1, let me at least find some elements of order D inside the copy of CM1. So M1 equals D S1, let's say. And we know that A1 generates this CM1. And so we have that E A S1 A1 2S1 A1 all the way up to D minus 1 S1 A1 have order D. Again, I stress when I'm not using this word order in the standard way, I'm using it just to mean the Dth power, or as in this additive notation, if I multiply by D, I'll get to the identity, but I should have called that 0. Similarly for CM2, we have E S2 A2 up to D minus 1 S2 A2, where of course M2 equals D S2. Well, I'm already done because I can then just look at all elements of the form. I could actually, I just got D of these and D of these, and the overlap will be in just one place. So I've got 2D minus 1 already. But let me just get a slightly bigger supply of elements. So I can just take all elements of the form. Again, what letter shall I go for? H S1 A1 H dashed, or it's horrible notation, but H dashed S2 A2 0 0 0, and then I've got a nice collection of D squared elements that all have D powers equal to the identity. I have now written 0 instead of E. Okay, so that actually solves the problem if we assume the classification of finite abelian groups. But what if we don't? So how can I characterize a non-cyclic finite abelian group? What does it mean? Well, let's suppose that G equals, we've got the letter N already, so let's call it capital N. So the difficulty here is that it's a sort of negative thing. So there is no, or perhaps I'll put it this way. For every A, there exists M less than N, such that A to the M equals the identity. I've gone back to multiplicative notation now. But we also know something sort of by Lagrange. If A to the M equals E, then M divides N. So this actually could be a completely different root. So we can strengthen this to say for all A, there exists M such that M divides N, M doesn't equal N, and A to the M equals E. So if false, so if the result is false, then that should put an upper bound on the number of elements. Then let's now let O of A be sort of actual order of A. So I'm not going to use the false assumption just yet, but we know that G equals the sum over all D divide N of the number of A such that OA, the order of A, equals D. Now, either we've got something, I'm going to try something a little bit weak at this point, or am I? So if at most D elements A, if for all D, that is, at most D elements A satisfy A for D equals E. So I'm going to do a sort of a crude upper bound that the number of things with order actually equal to D is at most the number of elements that satisfy this equation, but in fact it's smaller than that because some of them don't actually have order E. So then we get that G is less than or equal to the sum D divides N of D. And this is a well-known expression, or is it? So I'm more used to the expression sum D divides N over D. I think, but what do I want to do here? I feel as though some very basic number theory has temporarily escaped me, so I'm just going to try putting 12. What is the sum over all D divides 12 of D? It equals, so it's the sum of the divisors of 12. I get 1 plus 2 plus 4 plus 6 plus 12. If I also add in the assumption that D is not actually equal to N, I can get rid of this 12 part, and I get something that's still bigger than 12, no contradiction. So I will use the what I'm supposed to use. So instead of, there's a number of elements of order actually equal to D. So going back to here, it equals, oh, wait a minute. So in a cyclic group, this would be just 5 N over D, I believe. Ah, so we've established that this is not strong enough. But okay, so maybe I should ask myself the following. If at most D, let's say if for all D, at most D elements satisfy A to the D equals E, then how many elements can have order D? And here I've been missing something very simple to observe, which is that if A has order D, then all of 1A, A squared, A to the D minus 1 they're distinct and they satisfy x to the d equals e. So they are all the solutions. That's on the assumption that that most d elements all satisfy this equation for every d. So the number of elements of order exactly d is just the ones that are co-prime to d, so phi of d. So in fact, we have that G equals the sum over all D divides N of 5D, or rather it's less than or equal to because if there's an element of order D at all, then it'll be 5D, and if there isn't an element of order D at all, of course, it'll be 0. And now this, I believe, just equals N. But I need to check that. So I think it's easy to see that it's, so if I've got a cyclic group, if I have a cyclic, okay, so that this, we have equality if G is the cyclic group of order n. Why is that? It's because in every element of Cn has to have some order. The number of elements of Cn of order d is you just pick one element of order d, and then you'll get phi of d, and yeah, you just the element of order d will you just pick n over d, for example, and so you get phi. So you get equality of g equals Cn, and therefore this number equals n. And so we must have equality. So since we also knew that n was just supposed to be the size of g, so we must have that this equals this. But that means that we have to have equality all the way, which means that we can't just throw away the term when d equals n. Because you remember that we got that this inequality holds because the number of elements of order d is at most 5d. And if G is not cyclic, that would tell us that there is no element of order n, so that the phi of n term here would not be there, and we'd have a strict inequality, and that would be a contradiction. So must have equality. So number of elements. So that's not the key point. And also equals sum d divides n, the number of a such that the order of a equals d. So number of elements of order n in particular is, so we've got inequality all the way through, because this number here is at most 5D. So the number of elements of order n is 5n to not 0, so G is cyclic. Okay, that'll do. I will stop. And thanks for listening. It took a bit, it was a bit sort of clumsy as it needed to be, but got there in the end.